Okay, this is MA 161's a Fall 2021 Exam 1. This is actually, we are starting to, this is the semester I took this class. I took Calc 1 in the fall of 2021, so I kind of remember some of these questions, which is kind of weird. Most of these are like, oh, they're new problems that I've never seen before, but now I'm starting to get to ones that are like, oh, I have a vague semblance of immediately how to do this. So maybe that'll help out for these. So starting question one, typical question one, domain problem, figuring out the domain of this function here. So let's find that out. The first thing we need to remember for domain problems is what they are. Domains of functions, they are basically just the values of x, or the set of values that you can plug into x that'll still make the function valid and defined. So imagine a situation where we had like this is an example function g of x equals 1 over x. Imagine if that x was a 0. Well, then we would have 1 over 0, and that's undefined. That it approaches infinity, but it's not defined at anything at x equals 0. So in this case, the domain of g of x goes from negative infinity, skips over 0, and then goes on to positive infinity. So basically what that says is you can plug in any number, any number from negative infinity to positive infinity, except for 0, because it skips over 0, because if you plug in 0 here, it makes it divide by 0. So we're just looking out for little things like that can make our function undefined. There are, I like to call them the main three. There's usually three types of um, things in functions that can cause restrictions. The first one we just said is if you have in the denominator, if you have a denominator or like a fraction or anything, that denominator cannot equal 0. Another common one is the square root. You know that when you take the square root of something, it can't be negative, else you get an imaginary number. So when you take the square root of something, it cannot be negative. So it must be greater than or equal to 0. And then a third one, which is a little more obscure, but it's actually going to come into play in this problem, is logarithms. So when you're taking a logarithm of something, that something, it must be positive and must be greater than 0. It can't be negative and it can't be 0. So those are the main three restrictions. It looks like all of them are going to appear here in this problem because we have a fraction, we have a square root, and we have a log. So we've got all three of those to worry about. So let's start dissecting this. You can really do any three of these restrictions in any order you want. I'm just kind of going to go from the way that I said it first, from top to bottom here, so it's just a little more clear. So starting with the first one, the fraction, whatever's in the denominator, cannot equal 0. So the denominator cannot equal 0. 1 minus x squared cannot equal 0. All right, so now we're going to solve for x. Subtracting 1 from both sides, you get negative x squared cannot equal negative 1. Multiplying both sides by negative 1, we get x squared does not equal 1. And then taking the square root of both sides, we get x cannot equal plus or minus 1, I guess. Since we're taking the square root, I guess it can be a plus or minus, but that might spell weird news for when we actually try to find the actual domain at the end, but we might not have to. So we'll figure that out when we get there. For now, I'm just going to leave it with the plus and minus. X cannot equal plus or minus 1. All right, so we've done that first restriction now. The second one, we have a square root. So remember what we said, anything that's inside the square root must be greater than or equal to 0. So whatever's inside the square root, 1 minus ln of x, must be greater than or equal to 0. So now we solve for x, subtract 1 from both sides, negative ln x is greater than or equal to negative 1. Flip the signs of everything, so ln of x is greater than or equal to 1. And then what we can do now is, whoa, actually, hang on, I made a mistake. So keep this in mind when you're dealing with inequalities, things where you have a less than or a greater than. If you are multiplying or dividing by a negative number, as we just did here, where we multiplied both sides by a negative 1, you must flip the sign. So this greater than sign needs to become a less than sign. So whenever you multiply or divide by a negative number, you flip the sign of the inequality. All right, so now we're here. How can we get this ln x into just a vanilla x? We can actually treat all these as exponents, as like e to the ln of x and e to the 1, and this will get rid of the e and the ln on the left here, and we're just left with x. So now x must be less than or equal to e. So that's our second restriction, x is less than or equal to e. And now we just have one more. So we have this logarithm up here. So this logarithm, whatever's inside the logarithm, must be greater than 0. So the inside here is just x, must be greater than 0. Oh, cool, we didn't even have to do any work. Didn't have to simplify and get x all by itself. It's already by itself. So x must be greater than 0. All right, so now we have our 3 restrictions. We just need to put it in a form that it likes to see. So which one of these looks correct? I think A looks good. I think A is the right one because, so look at what this is saying. X cannot equal -1 and it cannot equal +1. Does this exclude -1 and +1? Yes. -1 is less than 0 and it goes up from 0, so that's covered. And it looks like it skips over +1. So we've got the -1 and the +1 covered. It is less than and greater than e, less than or equal to e. Sorry, I'm getting my words mixed up. That's covered there, and we also have x is greater than 0, which is right here. It's not a greater than or equal to sign because it is a parenthesis on the end there. So A looks good, but since this is more of an abstracty problem, I think it'd be good if we ran through B through E as well and make sure we've got the right one. So B, this one's wrong because it accidentally included +1 in its domain. It's saying that the values from 0 to E are all good, but remember we need to exclude +1, so B must be wrong. C is, what about C? C is wrong because it includes 0. We said on the right here that 0, x must be greater than 0. X cannot be anything less than 0, and because it includes numbers between -1 and 0, we know it must be wrong. D is actually, so the domain of D is okay. Like if you plug in any numbers of D's domain into f of x, you'll still always get a right answer, but it is wrong because it is not general enough. It's too specific because it forgot to leave out this other segment here, the numbers from 0 to 1. Because it forgot those, D must be wrong, even though its domain is technically kind of correct. And then E is also wrong, again, for the same reason as C, because it accidentally included numbers between -1 and 0, which we said cannot happen. So E must be wrong. We know that A is the right answer here. Question 2. This is one of these like functions within functions within functions problems that kind of comes up. I'd say maybe on like half of these exams, so it's probably a good idea to know this. Usually it just gives you a few different functions. Looks like we've got 3, f of x, g of x, and h of x. And it wants us to put them all together in a certain order. So looks like it wants us to put h inside of f and then inside of g. So that's what that circle means. When you've got a circle there, it just means this is just g of f of h of x. How many parentheses is that? 3. Okay. So that's what that means. We just put one function inside another, and then whatever we get at the end is going to be our answer. So let's start with that. I'm going to rewrite that because that's good to know. G of f of h of x. So we'll start on the inside and then expand outwards. So we'll first start with figuring out how to put h of x inside of f of x first. So if f of x is x squared plus 3, we need to put ln of x inside the x there. So this is now g of, so the x now of f of x needs to be ln of x. And then this is now squared plus 3. So there we go, we've got the inside now, and now we need to put all of this inside g of x. So we need to put it inside the x of the 1 over 7x minus 1. So Putting that in there, we get 1 over 7 times ln x all squared plus 3. And yeah, that's actually where I'll... Are we done at this point? Hang on. Oh, no, we've got that minus 1. All right, so yeah, are we done at this point? Is this one of the answers? Oh, it is really close to C. So if you look at C, it's like uber close. It just wants us to multiply the 7 out. So if we do that, we get 1 over, this becomes 7 ln L, oh, that's I combined L and N, ln x squared, uh, extra parenthesis, uh, plus 21 minus 1, which becomes plus 20. So that's how I got the answer of C. So yeah, just these, as a recap, I like to kind of do that at the end of problems. As a as a recap, yeah, just these functions inside of functions problems. Just remember what these circles mean right here. Just means the right is put into the left. And then you can just combine it like that. Sometimes it might ask you to do like, so it just asks us to find the full function, but maybe it wants us to put in like 3 for x right here and then solve that. But in this case, it didn't ask us to do that. But if it does, it's not the end of the world. So there you go. Okay, question 3. This is a properties of logarithms questions. So, um, properties of logarithms are just the things that you can do with logarithms to kind of change the way they look and how their exponents and their coefficients are just present and in what order and whatnot. You can, in using them, you can kind of change what a lot of logarithm functions look like. And sometimes, in this case, we're going to use a lot of them to figure out what things equal, like even if you don't know what this like base b is. So what it's saying is it gives us two definitions for these two abstract logarithms with this like base that it never defines or specifies. And then it gives us this bigger logarithm with that same base, and it's asking us to figure out what it equals. So the way we're going to do this is with these big three properties of logarithms. So similar to question 2 that I just did, where there's, no, question 1, where there's like a big three properties of domains that you should know. There's also kind of one with logarithms. There's 3 properties of logarithms that come up quite often. So the first one is if you have 2 logs of the same base that are being added together. Actually, I should not do a and b. I should do, let's say, x and y. This just equals 1 logarithm of that base, with them being multiplied together on the inside. And vice versa. So if you have 1 logarithm with something being multiplied on the inside, you can separate it into 2 logs being added together. So that's the first one. The second one is kind of the same, but with a minus sign. So if you have 2 logs being subtracted, so log base b of x minus log base b of y, it is 1 log where they are being divided. And of course, you can go the other way around too. If you've got 1 log with something in the middle that's a fraction, as we have up here, that's probably the first thing we're going to do. Then you can go the other way around and split it into 2 different logs that are being subtracted. And then the third one, which is different from both of these, if you have a log that has an exponent at the front, I'll use c, then you can actually take that coefficient c. Sorry, did I just say exponent? I'm sorry, I mean coefficient. If you have a coefficient on the left side there, you can actually take that coefficient and make it an exponent. I think that's where I got mixed up. So log base b of x to the power of c. And you can do vice versa as well. So those are the big 3 properties of logarithms that come up in these properties of logarithms questions and in calculus as a whole. So it's good to know them, and we're going to use them to pick apart this expression here and figure out what it equals. So again, like I said, the first thing we should probably do is we see we've got this fraction on the inside, and that is what we said here. If we have a fraction on the inside of a logarithm, we can split it up into 2 different logarithms. So doing that, we get log base b of the top, which is x squared times y to the 1/3, minus log base b of the bottom, which is the square root of x. So there we go. Now we've got this. Before we move on to the next step, I'm actually going to rewrite this square root of x as x to the 1/2 power. I think it will, yes, we actually do have to do that because in a later step, we have to use the third property that I said, and we're going to put that as a coefficient. We can actually do that right now if we want. Minus 1/2 logarithm base b of x. And now we have that. So, but before we move on to what we do after that, we have to do this. So we've got this logarithm now with two things on the inside being multiplied. And what we said earlier, if the inside has two things being multiplied, we can do two logs being added. So this is now log base b of x squared plus log base b of y to the 1/3. So now we have this. At this point, we can do the third property for these first two terms. We can bring all of their exponents out to the front, make them coefficients. So this becomes 2 log base b of x plus 1/3 log base b of y minus 1/2 log base b of x. All right, so now we're here, and we'll see that we have log base b of x, log base y of x, and log base b of x. Wait, log base b of x, log base y of x, log base b of... Wait, I'm getting really confused. Hang on. I keep jumbling over my words. We have a log base b of x, we have a log base b of y, and another log base b of x. And we'll see on the top left, we've got definitions for those three. Log base b of x equals 4, and log base b of y equals 9. So we can go ahead and substitute all of them, and we'll just be left with a bunch of numbers that are being multiplied and added. So this becomes 2 times 4 plus 1/3 times 9 minus 1/2 times 4. Putting this all together, we get 8 plus 3 minus 2, which equals 9, D. So yeah, this is why these are actually kind of my one of my personal favorite topics in these in calculus, because it's A, it's used a lot in calculus, so it's important to know, and B, it's kind of fun, just like taking this big ass logarithm we had originally and condensing it down into literally just one number. I think it's just satisfying seeing all this chaos kind of be nice and like orderly and condensed like that. So I don't know if you are kind of thinking of it that way, but I like the way that it goes. Again, just to do these problems, just remember these big three that I said, where you got the different logs being added and subtracted and like has a coefficient and stuff. You can like rearrange them in different ways and really crunch down those logarithms into something smaller. All right, question 4. Cool, an inverses problem. So this looks like a classic inverses problem where we're given a function, f of x, and then we're asked to find its inverse and then plug in 2 into the inverse. So, all right, how to find inverses. First, rewrite the function, but with a y instead of an f of x. So this is y equals 5 over e to the x plus 1. And now we are going to swap the positions of the x's and the y's. So this y becomes an x, and this x becomes a y. Now at this point, we are going to we are going to rewrite this equation back into a form where we have a y all by itself on one side, and then whatever's remaining is going to be our inverse, f inverse of x. So that's what we're going to do now, trying to get y all by itself again. So to start, I think we could multiply, we can multiply both sides by e to the y plus 1. So we get x times e to the y plus 1 equals 5. And then we can divide both sides by x to get e to the y plus 1 equals 5 over x. So now I've got this e to the y term kind of all by itself, and then if we were to subtract both sides by 1, it makes it even clearer. We've got e to the y equals 5 over x minus 1. So now we actually have e to the y all by itself. And now what we can do, we can take the ln of both sides. So when we take the ln of both sides, remember what I just said in problem 3 of this exam, where if we have an exponent, inside of a logarithm, we can actually take it outside and move it and make it a coefficient of that logarithm. So applying that logic, we will get, see on this left side, this is going to become y times ln of e. And ln of e is just 1, because the log base b of b always equals 1, and ln is just log base e. So, all right, that was actually, now that I said it out loud, that's a little confusing. Let me actually write this out so it's clearer. If you have log base b of b, that always equals 1. And since ln just equals log base e, log base e, no, ln of e just equals 1. So that's what I just did here. When we take the y and move it outside, this becomes y times ln e, and then this ln e is just 1. So that's what I did there. Now what we do is figure out why my taskbar is not disappearing. Oh, there it goes. Okay. So y equals, now it's, whoops, ln of 5 over x minus 1. So here we go. Now we've got our inverse. F inverse of x equals ln of 5 over x minus 1. So now what we do at this point is we just plug in 2 for the x's, and we will have our value. So let me rewrite this a little bit. F inverse of x equals that. So now F inverse of 2 equals ln of 5 over 2 minus 1. This equals, let's see, this will be ln of 2, this will be 3 halves. So ln of 3 halves, which is, oh, okay, 3 halves just equals 1.5. So ln of 1.5. That's so weird. Like, you don't really see a whole lot of decimals in Purdue calculus, at least, like at all. So seeing the decimals here is a little weird, but I mean converting fractions into decimals and vice versa is not that tricky. So it's like not, the most annoying problem in the world, but it's just weird seeing it here. But yeah, this was an inverses problem, a classic inverses problem where you just remember how to do inverses, which is where you substitute the x's and the y's with each other, and then solve for y, and then whatever's left is the inverse. That's how you find them, and then yeah, sometimes you'll just be asked to plug in values after that. Question 5. Actually, before we do that question, let's answer the question of why is this thing not going away, this top bar. Usually just fades out. There it is. All right, question 5. How many values of theta in an interval from 0 to 2 pi satisfy the following equation? So we've got this equation here. What it's saying is how many values for theta that are between 0 and 2 pi still make this equation valid. So, all right, this is more of a like conceptual, like knowledge test kind of question. Like it's just probing you on what, like, do you know enough about sines and cosines and trig functions and how they go about their business on the unit circle? If you do, then you'll probably get this one pretty quickly. So I'm going to do more of a visual approach in explaining this problem. There's still going to be a little math involved, but I think graphing this out and using the unit circle is going to be easier to explain how to solve this one. So before we do that, I'm going to simplify this equation. I'm going to get cosine of theta all by itself. So to do that, we can add 3 on both sides. So this becomes 12 cosine squared theta equals 3. Divide by 12 on both sides, we get cosine squared theta equals 3 divided by 12 is 1/4. And then square root of both sides, cosine theta equals plus or minus 1/2. So now we have cosine theta all by itself. So now we just need to figure out what values for theta here make the cosine equal positive or negative 1/2. Okay, so this is the graphing part now. I'm going to show this visually. Sorry. I'm going to make a big unit circle. This is the unit circle where it starts at 0, midpoint is pi, and then loops all the way back around at 2 pi. That is a unit circle. And remember, whenever you have like an angle, like let's say an example angle right here, theta equals, let's say, this kind of looks like 5 pi over 6. Whenever you have an angle like that, when you take the cosine of it, it's just asking for the length of this line. What is the length of this line here? And that's why sine and cosine never go beyond 1 and never go under -1, because the length of this line can never exceed 1. The maximum length is right here is actually -1. Maximum length is 1 here. So that's why they're never beyond 1 and -1. All right, but going back to the original problem, how many values of this theta, how many arc lengths here will make this line equal plus or minus a half? So we can see here that, I mean, we don't really need to know what theta values correspond to a half. We can just imagine the same arc length for all of these. Not same arc length, the same line length for all of these. We got plus and minus a half here. These are the these are the 1/2 right here. And these are the negative 1/2 on the left here, because cosine is negative on the left and positive on the right of the unit circle. And there, it looks like we've got 4 different angles that we can use here, because if we draw lines going back up for all of these, we've got an arc length here, got an arc length here, got an arc length going all the way around here, and then an arc length going all the way around to right here. So it looks like we've got 4 here, and so our answer will be 4 values for theta. I hope that was a convincing enough explanation. I just used a unit circle here. As long as you are comfortable with the knowledge of like how arc lengths and trig functions and that line I was talking about, like this line here, and what that means, which is just, you know, the value of trig functions. You should be good to go on this problem. I just sort of explained it in a more visual manner. Okay, question 6. This question is actually so tall because there's a graph here that I had to zoom out kind of a lot. So apologies if the text is a little harder to read. I just wanted to make sure that I fit like the full question in the frame to make it easier for the types of students that like just scrub through the YouTube video and then kind of take notes on like a paused frame of it. So I wanted to make sure that they're accounted for. So. All right, so for the function graph below, which of these 4 statements are true? So let's run through them, see which are true, which are false. Statement 1, f of 2 is defined. So we have f of 2, or no, we just have 2. We have x equals 2 right there. What is it defined at x equal, actually not even what it's defined at, is it defined at all? And yes, it is. It's defined right here. We've got that filled in black point there. That means it's defined at that point. Looks like it's defined at 1, y equals 1. So, yep, it's defined there. What about statement, you know what? Instead of doing statement 2 right after, I'm going to do statement 4 because it is actually just it's kind of an easier version of statement 2, and it's sort of in the same kind of topic. So by doing statement 4 first, it'll make statement 2 easier. So statement 4 is the limit as x approaches 2 exists. So does the limit as x approaches 2 exist? Well, okay, for general limits, which is just limits that aren't one-sided, which this is, you have to consider the left-sided limit and the right-sided limit. So the only way that the general limit can exist is if the left-sided limit and the right-sided limit both approach the same value. So we'll see here the left-sided limit looks like x is approaching this point, which is like y equals 1. And the right-sided limit looks like x is approaching 2 here, or as x, well, I don't know how you'd say it, but as x approaches 2 for the from the right side, looks like that's going to equal 2 instead. And since those are 2 different points, those are 2 different values, it means that the general limit as x approaches 2 does not exist. So now, knowing that, it makes statement 2 easier. the limit as x approaches 2 equals 1. Well, that can't happen because the limit doesn't even exist. You can't have it approach a value and not exist at the same time. So that's also out. We're just left with statement 3. So statement 3 is one of these one-sided limits. It's as x approaches 2 from the left side. So we'll just look at that side there. What value does it approach? It looks like it's approaching this point right here, which is y equals 1. That's a 1. So yes, statement 3 is true. So B is our answer here. So there. Yeah, just a kind of a conceptual limits question. I think I'll probably still throw this under like the limit topic, like I'll include it there, but maybe I'll also do like continuity or whatever topics I'm going to choose later on. So this is a kind of a jumble of a couple different topics in Calc 1. But yeah, as long as you're comfortable with your like the difference between general limits and one-sided limits, actually they probably call it two-sided limits, um, then this problem is not too tricky. So there you go. Okay, question 7. This is the first limit problem on this exam, which is great because there's like, I think I looked ahead, there's 4 limits on this exam, which is pretty standard, but still it's just a lot. Like a third of your exams are like one topic. It's just like, if you don't like limits, it's just like a drag to keep doing these. So anyways, all right, this first limit here, limit as x approaches 2 of all this big fraction. So, all right, so what I recommend doing for every limit every time is just to plug in the number that x approaches and then just see what happens after that. Usually you can get a good idea of what to do afterwards, how to solve the limit once you plug in the value. So, plugging in 2 for all of these x's here, we get 2 minus 2 all over the square root of 3 times 2 plus 10 minus 4. This is equal to 0 over, let's see, it'd be 3 times 2 is 6, 6 plus 10 is 16, square root of 16 is 4, and 4 minus 4 is 0. So we have an indeterminate form now, and what that tells us is that we can do L'Hopital's rule. So what L'Hopital's rule means, like what you can do with it, is if your limit evaluates to either 0 over 0 or infinity over infinity, then you can do L'Hopital's rule, which is where you take the derivative of both the top and the bottom, and the limit won't really be affected at all. You can still plug in the value and you'll get the correct answer. So because we have an indeterminate form, we have 0 over 0, we can go ahead and take the derivative of both the top and the bottom now. So derivative of the top, this will just become 1 because the derivative of x is just 1, and then derivative of minus 2 is just 0 because the derivative of any constant is just 0. So this will be, I'll just write it as 1 over a big thing. All right, now the derivative of the bottom, well, we can already kind of just forget about the minus 4 because it's a constant again. That'll just become a 0. And now we just have to take the derivative of this square root right here. So it's a little harder because it's a big square root with a bunch of stuff inside of it. It would be a lot easier if it was just like the square root of x instead of the square root of 3x plus 10. But it's still not the hardest thing ever anyways. So square roots are just the same as powers of a half. So 3x plus 10 to the power of a half. This makes it clear that we can do the exponent rule, like the derivative exponent rule, where we kind of take it out to the front and then reduce its power by 1. So this now becomes 1/2 times 3x plus 10 to the negative 1/2 power, because 1/2 minus 1 is negative a half. And now, since we took the derivative of like something that's not just a vanilla x, we took the derivative of this big thing here, we have to multiply it by the derivative of the inside, which is 3x plus 10. So derivative of 3x plus 10 is just 3, because the derivative of 3x is 3, derivative of 10 is 0. So that is the L'Hopital's rule-ified limit that we have now. Now it looks like if we were to just plug in 2 here, it wouldn't be an indeterminate form anymore, and it wouldn't like divide by 0 or anything. So let's try doing that now. So we'll get 1 over, um, actually, hang on. Before we do that, I'm going to rewrite it just a little bit. I'm going to put this term here, this 3x plus 10 to the negative 1/2 power, I'm going to put it on the top. And then, so its power sort of flips around. It becomes positive again. So this is going to become 3x plus 10 to the positive 1/2 power now, all over 1/2 times 3. And what this 1/2 power means, again, is it's just a square root. So this all becomes a square root. So now it's in a much easier to understand form, just to plug in the 2 now. So this will become the square root of 3 times 2 plus 10 all over 1/2 times 3. This equals, on the top it'll be 6 plus 10, which is 16, square root of 16, all over 1/2 times 3. This is 3 halves. This is the same as dividing by 3 and then multiplying by 2 on the top, which equals 2 times, this will be 2 times 4, so 8 over 3. And this is C. Is that actually the right answer? Because I don't think I looked at the answer key for doing this problem. So let me check real quick. 7 is C. Wonderful. All right. Where were we? Here we go. All right. So yeah. So limit problems. This was a L'Hopital's rule problem where if you ever get an indeterminate form, which is a 0 over 0 or an infinity over infinity, after plugging in the value, you can do L'Hopital's rule, which is basically you take the derivative of the top and the bottom, and it doesn't affect the limit at all. So once you do that, you can just go ahead and plug in the value, and you'll get your answer. All right, question 8, another limit problem. So this is the limit as x approaches 4 of this big fraction. So you're looking at, there actually might be 2 different ways to solve this. I'm going to do what I always recommend, which is to plug in 4, and we'll see what we'll get. I think it's going to be an indeterminate form, where we have like 0 over 0. But there might actually be a simpler way to do this that I think I'll explain after. So for now, I'm going to plug in 4 and see what we get. So this will be negative 4 plus 1 squared plus 25 all over 4 minus 4. This will become, on the bottom is 0, and on the top, see, it's going to be 5 squared, or negative 5 squared, which is 25. So negative 25 plus 25 is 0. So yeah, we have an indeterminate form now. We could probably do L'Hopital's rule on this and then get our answer that way. But what I think is a lot easier, actually, is realizing that if you were to take the numerator here, and we take out this minus sign at the front. If we kind of multiply everything by a negative and then put it out front to make it look like this, so x plus 1 squared plus 25, or no, not plus 25, it'd be minus 25 now. This is now a difference of squares. So you'll see that this first term here, this is being multiplied, or this is as an exponent of 2, so that's a square. And then this second term here, 25, that's a perfect square. So it's 5 times 5. So since we have a difference of squares, we can actually split that up into 2 different terms, and one of them will probably be this. It'll probably be an x minus 4. So let's do that. Doing L'Hopital's rule like over here, yeah, again, it would probably work because this bottom part, this denominator, would simplify down to just 1 and be dividing everything by 1. So yeah, it'd probably work out, but I'm going to do it this difference of squares way because literally the previous problem was a L'Hopital's rule limit. So I'm going to do something a little different, cover a lot more bases this way. So this difference of squares, it becomes, the square root of each term being added and subtracted in each term. So this becomes, we got the minus out front. Now we have x plus 1 minus, or plus 5, and then x plus 1 minus 5, all divided by x minus 4. This will simplify down to the first term becomes x plus 6, second term becomes x minus 4, all divided by x minus 4. These two terms will cancel, and we're just left with negative x plus 6. So now if we were to plug in 4, we would get negative 4 plus 6, which is negative 10. So that's, I think, the easier way of doing this problem instead of having to do L'Hopital's rule and doing a derivative, which you might not be fully comfortable with yet because it's just your first midterm. Just realizing that you can make a difference of squares up there and uh, do that sort of like easier term cancellation thing where you kind of get rid of the trouble in the denominator that makes it all divide by 0. So I think that would be the easier way of doing this problem. But L'Hopital's rule would still probably work. In fact, I actually think I'm going to do it really quick just to show you that there's multiple ways of doing some of these limits. So it looks like the top part here, looks like it will multiply out to negative um, x uh, x squared plus 2x plus 1, and that's minus all of that, so negative x squared minus 2x minus 1 plus 25, so this would be plus 24 all over x minus 4, but that'll all get like canceled because when you take the derivative of the denominator, it's just going to become 1. So you can ignore that. Derivative of this now, I'm going to put it down here. This will become 2x, or negative 2x minus 2, and when you plug in 4, this becomes negative 2 times 4 minus 2, which equals negative 8 minus 2, which equals negative 10. So yes, there are multiple ways to do these problems, but some are easier than others. If you are more comfortable doing derivatives, then L'Hopital's rule is easier. But you can also just realize again you have the difference of squares up here, and you can do it that way. So different ways, different strokes for different folks. That's a good like motto for this problem, I guess. All right, question 9, another limit. I think this is the third limit out of 4 limits on this whole exam, so we're halfway done now. So the limit as h approaches 0 of this fraction here. So I think this is actually going to be pretty similar to question 8, like the limit that we just did, where you can approach this using L'Hopital's rule. I think if you were to plug in 0 in for all these h's, you would get 0 over 0, and you can do L'Hopital's rule. But I think there's an easier way to do this because if you kind of look at this whole thing, look, it's a limit as h approaches 0 of something with just an h on the bottom and two things being subtracted on the top. That is eerily close to the limit definition of the derivative. If you forget what that was, it's the definition here when you have f prime of x, the derivative of x, that's just the same as the limit as h approaches 0 of f of x plus h minus f of x all over h. That's the limit definition of the derivative. It's a different way to do derivatives. And these two are really, really similar. So I bet there's a way to actually kind of take this and figure out what the original f of x is and then just take the derivative of it. I think that would be easier to do. Looking at it, I think the easiest tell is realizing that these two are just meant to be f of x's but with different things put inside of it. So it's not the easiest way to explain it, but I think the original f of x was 1 over x, and the value that it was trying to find it at was x equals 8. Because if you do that, you'll end up getting, so if you do f of x plus h, as you have to do in the first part of the limit definition of the derivative, you'll get 1 over, it'll be 8 plus h, which is exactly what this is. So I'm pretty sure that was the original f of x and the original, x value that it was being found at. So knowing what f of x was, we can just take the derivative of it, and then plug in 8 afterwards, and then that'll be our answer. So I think that's an easier way to go about this problem than to do L'Hopital's rule, which have you do two derivatives at the same time. So let's go ahead and do that, taking the derivative of this. Not too bad. You just have to remember that 1 over x is the same as x to the negative first power. So when you do that, power rule, that exponent rule, where you bring it out to the front, that just becomes negative 1 times x to the negative 2 power. Negative 1 minus 1 is minus 2. And that equals, you have negative 1 on the top, and then since we have a negative exponent, you can go ahead and make it positive and then put it all on the bottom. So this becomes x squared now. So now when we go ahead and plug in 8, we will get negative 1 over 8 squared, which equals negative 1/64. So yeah, just another example of how understanding other aspects of calculus and other things that you studied throughout like your time taking calculus can make some of these limits easier. Instead of just leaping headfirst into doing a big L'Hopital's rule problem, you can just realize, oh, this is the limit definition of the derivative. You can kind of just cheat it and figure out what your original f of x was, and then just go from there, taking the derivative of just that instead, which is a lot easier. Okay, question 10. I think this is the last limit on this whole exam, so woohoo, no more after this. Find the limit as x approaches 4 from the right side. So that's a little bit different. It just basically means that let's say we have a limit or a function that looks like this. This is not what this looks like. It's just an example that I've done here. The right-sided limit, that's what the plus means, the right-sided limit just means that you only look at the right side, the value that x is approaching from the right side. And it looks like in this example, this function is going up all the way until infinity, so the limit would be infinity. If it was x as approaches it from the left side, it looks like it's approaching negative infinity instead. So that's just what one-sided limits means, like limits that are approach from the left or the right side. So, all right, figuring out this problem now. Um, it looks really tempting to go ahead and like split this numerator up into two terms that are being multiplied, and then you can like maybe one of those terms is going to be an x minus 4, but I don't think it's going to be that because if we do end up simplifying the top, I think it's going to be let's see. Uh, minus 2 minus 5, x minus 2, x minus 5, because minus 2 and minus 5 is minus 7 here, which, yeah, that's the simplified version of this. But none of these are, like, you can't cancel anything now. Like, you can't, do anything here. So instead of doing that, I think we're going to do actually what I recommend doing at the start of all of these, which is just plugging in the value here, 4. So this will become 4 squared minus 7 times 4 plus 10 all over 4 minus 4. This equals 8 minus 28 plus 10 all over 0, which equals 8 minus 28 is 20, and then plus 10 is negative 10 all over 0. So okay, this is one of those number line problems. So when we plug in that value that we had at the start and we end up getting something that's like infinity, like we get positive or negative infinity, where it's, divide by 0, but it's not indeterminate, where it's like 1 divided by 0 or 10 divided by 0 and something like that, then we can do the number line trick where we have a number line here. We have our middle value, which is going to be 4, and then we pick two values that are right on either side of it. So we can do, let's say, 3 and 5, and then figure out what those values are, just their sign, and then we can figure out if this answer is going to be positive or negative infinity. So that was a lot of words that I just threw at you. So if you're like confused, don't worry, I'm going to run through it. But that's essentially the big picture of this problem. Like if you're already understanding what to do at this point, you can feel reassured, like knowing that, hey, maybe I was thinking the right thing. But if you're still confused, I'm going to run through it right now. So If you were to plug in 3 into this, we would get, plug in 3, we get 3 squared minus 7 times 3 plus 10 all over 3 minus 4. So I'm going to say you never need to actually figure out the answer to this. You don't need to find the value. We're just trying to figure out what sign it's going to be at the end of all of this. We just need to figure out if it's going to be positive or negative. So this is going to be 6 minus 21 plus 10 all over 3 minus 4. That is a negative number. Let's see, on the top, it's going to be 6 minus 21 is negative 15, plus 10 is going to be negative 5. So this is going to be negative over a negative, which is a positive value. So you know everything that's going to be on the right, on the left of the 4 is going to be positive. So we're going to put a bunch of pluses here. Now we're going to do the same thing for the 5, for when we plug in 5 into the equation. So plug in 5 in there, we get 5 squared minus 7 times 5 plus 10 all over 5 minus 4 is going to be 25 minus 35 plus 10 all over 1, which is just 1. I'm actually going to erase all that. This is going to be now oh, okay. I made a mistake actually. I should have looked ahead because if we solve this, we are going to get 0. We're going to get 25 minus 35 is negative 10 plus 10 is 0. So that is not positive nor negative. I messed up. We should have done something that's even closer to 4. We should have done something like, what's 4.5? 9 halves, I think. We can do 9 halves instead. It'll make the work a little harder, but we actually will get something that's either positive or negative instead of just 0, which is unusable for our case. So doing this again, we get 9 halves squared minus 7 times 9 halves plus 10 all over 9 halves minus 4. The bottom is going to be positive this time around because 9 halves is bigger than 4. So something bigger than 4 minus 4 is positive. It's going to be positive over, let's see, 9 halves squared is going to be 81 fourths minus 7 times 9 halves. That's going to be 63 halves plus 10. You can see why sometimes you don't really want to use fractions. This is a little annoying to simplify now, but it's still doable. We just have to make everything the same base. So this is going to be 81 fourths minus, let's see, 63 times 2. I don't even know what this is off the top of my head. It's going to be 6, and then, no, it's going to be 126. Yeah, 126 over 4 plus, let's see, 10 times 4 is 40 fourths all over a positive value. This is equal to, all right, 81 minus 126. I'm actually going to do 126 minus 81. This is the same as 5, carry the 1. This is 12. 4, 45, negative 45 fourths plus 40 fourths all over a positive value. This is going to be a negative over a positive now because negative 45 plus 40 is negative 5. So it's going to be negative over positive, which is a negative value. So everything after the 4 now is going to be negative. And since we are taking our limit from the right side, the positive side, which is this side, we know our answer is going to be negative infinity. So that's how you do some of these limits where you have it's a one-sided limit and you're taking it from just either the left or the right side. You can go ahead and first confirm that your initial answer is one of the infinities. It's either positive or negative infinity. And then from there, you can do the number line trick where you put the value that you're trying to take the limit at right in the middle, and then 2 really close values on either side, and then figure out if they are positive or negative, and then you'll get your answer from that. Okay, question 11. This is one of these weird like continuity problems where it wants you to like find this value for C that makes everything continuous. It's different to find the answer to, but I think I know the intended path to the solution that these test makers wanted you to take. So I'm going to see if I can try to do that. So first off, what is this actually asking of us? So find the value of C here that makes this piecewise function continuous. So all right, first off, let's digest what this piecewise function is actually saying. So for any Actually, let's look at the bottom one first. Let's look at that. When x equals 3, f of x equals 6. So if we draw out a graph here, like this, when x equals 3, that means f of x equals 6. We know of a point right there. Now what the top is saying is that for every other x value, it's this function here with this unknown constant c, and we need to find that constant c that makes this top function basically cross through that point right there. Because I think for any other value c other than the right answer down here, it will have a path that does like not path through it. It'll be something like that instead. So to find that, I think what we can notice is that um, the reason it's piecewise is because if we were to just plug in x equals 3 into that, we would get, we get a dividing by 0 error. We'd get 3 minus 3 equals 0 on the bottom, so that's why it's kind of piecewise. So we can actually set up a limit for this. We can do the limit as x approaches 3 for that top function. And then, I mean, we can't really take this limit yet because we don't know what c equals, but we know that it must equal 6 because that's what we are trying to find. We need to fill that hole. We need to make that limit evaluate to 6 at that given point. So this is why I was saying this problem is kind of weird because it's like a backwards limit. You're kind of asked to take it in reverse. You're trying to find a value inside of the limit that you need to find out by knowing the limit's answer, which you've never really been asked to do before. So I think I've done this type of problem before, and I had no idea what the hell to do for it when I started out, but I thought about it, I kind of looked at it, and I realized that I think it's kind of one of those problems where it's like a difference of squares that you break up, you simplify into two terms, and then one of those terms is going to be x minus 3 that you can cancel out. So if we pretend like that's what's happening, where the top part here is a difference of squares, and one of those terms that'll come out of it is x minus 3, this will become, on the top, x minus 3 times x plus 3 all over the x minus 3 on the bottom, that one. We get, we cross these out, and we get x plus 3, which equals 6. And we will validate that that was what we were supposed to do because, if we subtract 3 from both sides, we get x equals 3, which, yeah, that was true. So what we can do with this information is we can multiply this back out and then figure out what c was supposed to equal. So if we FOIL that back out, we will get x squared plus 3x minus 9. These cancel out. We just get x squared minus 9. This was x squared minus c, so c probably equals 9. And we can go at it. This problem is pretty easy to check your work now because we can just set up the limit again and evaluate it. So if we do the limit as x approaches 3 of x squared minus 9 all over x minus 3, we can go ahead and evaluate that and see if we get I think 6. So we can do that. We can we have our sorry, I don't know what I'm thinking. I'm jumbling over my words here. It's going late into the night at 12:58 p.m. The difference of squares here will evaluate to x plus 3 and x minus 3 all over x minus 3. These two cancel out. We're just left with x plus 3. And when we plug in the original value, we get 3 plus 3, which equals 6, which is that. So yeah, we know we did things right. We found our value of c. which is 9. And actually, that's kind of another way you can find this problem, just through brute force. If you don't know what the hell I just said in these past 4 minutes, you can just plug in each one of these values into C and then evaluate the limit, and whichever one gives you 6 is your answer. So um, I think that's another way you can do this problem. Question 12. Woohoo, this is the last one. Let f of x equals, okay, we have a function that it gives us. It's that, whoa, what the hell? Why am I not using my trademark cyan? There we go. Let f of x equals 3x squared plus 12 plus 2x plus 5. Use the definition of the derivative to find f prime of 1. So this is the that limit definition of the derivative that I've used a couple times in this exam. You know, the one where it's like limit as x approaches, no, not x approaches, h approaches 0 of f of x plus h minus f of x all over h. You know, that. Use that to find the derivative. And not even actually fully do it, just kind of simplify it and see what it will end up as. So I guess that's their way of making sure that you know what the definition of the derivative is by not solving it, but just seeing what it simplifies to make sure you know what this is. So, all right, so yeah, that's not so hard to understand at least. It's just, you know, taking this f of x and plugging it into this, but with a 1 as x. So we can go ahead and do that. So this will become, let's see, f of x plus h. This will become f of 1 plus h, and f of 1 plus h in here will become 3 of x, so this is 1 plus h squared, plus 2 times 1 plus h plus 5 minus, ooh, I really should have written smaller. Let me go ahead and rewrite that. So this will become 3 of 1 plus h squared plus 2 of 1 plus h plus 5 minus, big parentheses here, 3 of 1 squared plus 2 of 1 plus 5. So there we go. The reason it's a 1 here instead of a 1 plus h because it's minus f of x and the x is 1. So that's why it's just 1 for all of those x's. And then on the bottom, we have our h. So I'm going to omit that h for now. We'll just remember to divide everything by an h at the end. If we were to just include that denominator for each of these steps, it would get really long and tall and might not even fit on this page. So let's just remember to divide by h at the end and we'll be all good. So simplifying this now, multiplying everything out, this is 3 times, let's see, distributing this squared in, we get 1 plus h plus, this would be 2h plus h squared plus 2 plus 2h plus 5 minus, all right, now we have this now, minus 3 plus 2 plus 5. So there we go. All right, even more simplification. Starting again, we get 3 plus 6h plus 3h squared plus 2 plus 2h plus 5 minus 3 minus 2 minus 5. There we go. So now we just have to, yeah, even more simplification. Put all these terms together. So we've got our 1h squared term here, 3h squared. Looks like we've got 2 h to the first power terms, 6h and 2h, adding those together we get 8h. And now we've got all these constants. So 3 plus 2 is 5, plus 5 is 10, minus 3 is 7, minus 2 is 5, plus 5 is 10. Wait, did I do something wrong? Because I feel like this should be 0. I feel like it should have been like negative 5 plus 5 instead. Did I do something wrong here? Hang on, hang on. We can recover. We can figure this out. We're big. We're strong. Yes, I did do that wrong. This is supposed to be a minus at the end. Okay, thank God it was right at the end. I didn't have to redo all this work. So, recounting everything, since let's make sure we didn't screw up again. 3 plus 2 is 5. Plus 5 is 10. Minus 3 is 7. Minus 2 is 5. Minus 5 is 0. So this is plus 0 at the end. And then remember, we have to divide everything by an h. Because of that, we've just been omitting it this whole time because it would have gotten really tall. So now we have 3h plus 8. So there we go. Yeah, this was just a question testing if you knew what the definition of the derivative was, which is just that. And if you know it, you just plug in the f of x and the x equals 1 for all of it, and you're golden. You just simplify everything after that. And with that, that is this whole exam. What was this? Fall 21, I think. Um, oh yeah, I actually split this up into two PDFs because it crapped out on me earlier, but uh, yeah, you can still view the whole video anyways. But this is a pretty good exam actually. This is the one that I took. It had a domain, it had completing the function questions, some properties of logs and inverse, uh, unit circle stuff, graphing, bunch of limits, and continuity and stuff. So yeah, pretty all-encompassing exam, pretty good study resource. There's some exams that just throw the weirdest stuff at you. It's usually the finals that do that, but thankfully we're not at the finals yet, so we're just doing midterms, which are usually easier. So this one was, I think, sort of in line with that.